And welcome to A3 dot point, and on this one we're constructing a diagram to illustrate the energy losses associated with digestion and metabolism in animals. So this dot point is quite an easy one and doesn't take long, but basically what we're going to end up doing is creating this diagram, and it shows the total energy that's in feed all the way through, and the losses that occur until the energy that an animal actually uses. So the animal's cells can actually use as energy to move, to grow, etc. So let's go to the start first. So obviously food that's eaten by animals has a certain amount of energy in it, and we measure this in, for humans, kilojoules, calories, megajoules maybe, for animals, in the amount that they require per day and the amount that's in feed. And we look at that in later dot points in a bit more detail. But we know that humans, for example, need roughly 2,500 calories a day just to kind of survive and for the body to function normally. However, we might eat more than that, or our body doesn't get every bit of calorie or every single calorie that we consume. Our body just cannot process all of it. Some of it, it comes out of waste as waste. So we're going to look at how that happens. So obviously we can measure the energy in feed, and the way of doing that is called a BOM calorimeter. It's a machine where the food is burnt basically, and the energy that comes from it is measured. And we know that total amount of energy in the food is known as gross energy. Okay, so only part of this gross energy in the food actually can be burnt by the individual cells, as I mentioned. We lose stuff along the way in the process of digestion. So normally the amount of food, an amount of food can be digested. Example, some fiber. An amount of food cannot be digested and ends up in the feces. And we know that there is energy in the feces because that feces can be used as fertilizer for other things that can use the energy that comes from it. So we know that out of the food that an animal eats, or a human, etc., that not all of the energy in that food ends up in the animal or burnt by the animal. There is some that comes out. And this is the first step. So this is the stuff that can't be digested. And the part that can be digested is known as digestible energy, which is pretty self-explanatory. So of the part of the food that is digestible, some energy is lost in urine, and in ruminants in the form of methane gas. They lose a lot in methane gas. The remainder of the energy from digestible energy, once you have subtracted urine and methane, is known as metabolizable energy. And this is the amount of energy that's available to individual animal cells to burn. And we have that down here. When energy is burned by the cells, heat is produced. So it's the same as a car burning fuel. The car will produce heat. The engine in the car will produce heat as a side effect. And that energy, heat has energy, and that's lost energy that does not make it to the cell, or the cells can't actually use it for production. So that is also lost energy. And it's lost the environment, and so the remainder of the metabolizable energy, once you remove heat loss, is known as net energy. This is the final stage of energy loss in the diagram, and the rest of the energy can be used for maintenance and production purposes in the animal. So if we have to summarize, gross energy is the total energy in a feed. Digestible energy is gross energy minus the loss in feces of energy. Then we have metabolizable energy, which is digestible energy minus urinary and methane energy. This energy is available to animals to use or to burn. And net energy is metabolizable energy minus heat loss. Net energy can be used for maintenance and production, or ME and PE, maintenance energy and production energy. So this is a little bit like having a job and getting paid. You have gross income, and that is the total amount that you make. So if you're in a job where you get paid by the hour, it's just how many hours you've worked times whatever you get paid per hour. That's your gross income. And then various things are taken out along the way, like, for example, tax, maybe some other salary sacrifice things, maybe some extra superannuation, etc., are lost before you get your net income, which is the amount that you actually end up with in your bank account. And I'm sure you're probably aware that the amount that you end up in your actual bank account, or your net income, is quite a bit less than your gross income before tax. So that's an example of that applying somewhere else as well. This is an important point to make at at this time. So what the difference between maintenance energy and production energy is. So maintenance energy is the amount of energy needed to keep an animal alive and healthy, but does not allow for it to do anything else like grow, put on weight, produce milk, be pregnant, anything like that. So maintenance energy might be fed to an animal in a drought. So you provide it the minimum amount required just to be able to stay alive and not lose weight, not lose condition, etc. So that's a maintenance energy. Now, normally a farmer will want to feed, unless you're in a drought or something like that, you'll want to feed an animal production energy as well, which is extra energy, more energy on top of maintenance energy. And the reason is because it's not going to produce or do anything unless you feed it enough extra energy to be able to do that. And so additional energy for production, such as growth, pregnancy, lactation, producing milk, etc., that's what we term production energy. So they need to have in a ration, when you're thinking about a ration for an animal that's growing and you want to increase in its size or weight, or you want it to be pregnant, etc., you have to consider to give it maintenance energy and production energy. Okay, so moving back to this diagram, this is basically the key part of the dot point here. It's just a summary of what we've just talked about into a diagram. And often in exams, maybe half yearlies and trials will ask you to reproduce this graph, or in the HSC, it's been asked to reproduce parts of this before, but you certainly need to know this, the order and the things that are lost along the way, which we'll see in a second. So we have, as we said before, up top, gross energy, then you have minus fecal energy, which gives you digestible energy. Once you lose urinary energy and methane, you get metabolizable energy, and then once it goes to the cells, you lose heat energy when it's burnt, and you end up with net energy. So it's no coincidence that these arrows are getting smaller, because the total amount of food, the total amount of energy in food is a certain amount, and by the time they get to the energy that they can actually use in their cells, it is a smaller amount because energy is lost along the way. And these words down the side here are kind of what each step is titled. So you got the energy in the food, the energy absorbed by the body, the available energy to the cells, and then lastly, the actual energy available for maintenance and production. So you really need to know all of this table. Okay, so moving on to past HSC questions. They're mostly, if you know the table, they're pretty easy. This one down here is pretty hard, but we'll get to that in a second. The 2014 question, the diagram outlines the fate of energy associated with digestion, and it's really just reproducing two parts of the table here. Obviously, they could ask you any of these parts, and you need to know all of them in the order that they are. But here, once you have gross energy or total energy minus fecal energy, and then you have digestible energy minus urine and methane, and you end up with the third step, which is metabolizable energy. And the net energy ends up being used for maintenance and production. This one, 2012, is a harder question. It is question 20, which is always quite a hard one in the HSC. Hopefully it's the hardest one. And the diagram here shows how the total energy in a diet is used by an animal. So what you should do ideally to answer this question is you should draw out this table on the side here to answer the question to help you answer it. Obviously, you're not going to get marked on whether you draw anything here or not, but if you were able to reproduce the table and work backwards, you'd be able to work out this question. So what is metabolizable energy a combination of? So this energy here, what is it a combination of? So it's got metabolizable energy contains maintenance energy and contains production energy. So we've got production and maintenance of body function. So it definitely includes Y and Z. So we can rule out A, we can rule out C. It could potentially be D, and it could potentially be B. So this one here, heat and metabolic losses, well, it includes heat, but urine and methane here are considered metabolic losses. So this is actually lost before metabolizable energy. So this bit here means that it's not X, it's just Y and Z. So it's this one here, and the answer is B. This last question here is a very easy one. The fate of energy in the diet of an animal can be shown as following. You've got gross energy, then you've got digestible, and then metabolizable, and then lastly you have net energy. So it can only be C on that one.